façon, Lucas, il coupe
Ah, il
après le
coupe,
début et la
d'accord.
fin qui vont pas.
D'accord,
Et on peut démarrer le streaming aussi.
d'accord.
Voilà.
Ok.
Donc là, il faut simplement. Alors, la seule chose que tu peux régler éventuellement, c'est le volume du son. Enfin, tu vois, si le son paraît trop fort ici, ou le son pour les enceintes, tu peux les régler ici. Enfin, tu peux tout régler ici.
Mhm.
Le son. Mais en principe, c'est à peu près
Réglé.
réglé comme il faut, quoi.
Peut-être que j'efface les tableaux. Bon, merci.
Non, je vais rien demander.
Oui, à un certain
Ah oui, une
moment, je
télécommande.
voudrais oui,
Une
apprendre
télécommande.
un peu, comme ça je suis un peu plus indépendante.
D'accord. This is a Bluetooth remote, but we have first to perform a pairing. Okay?
So, it's Bluetooth. Okay.
Yeah.
We don't need the Wi-Fi and I want to close it. So we need this.
Alors, do you see something? If you add a new device, you should find it.
It's looking for something like that. You can maybe close and
No?
Qu'est-ce que c'est le problème? What's the problem?
is it sending?
Yes, normally, yes.
Maybe we can go here. Maybe it's one of these.
Okay, this is that one.
Okay.
For the pointer,
Yes, yes.
I don't know.
No way. So,
Okay, but if I have just a laser, I think, okay, we miss...
I will try to find another kind. I think we have another kind of remote.
Ok, se no il
Ma
laser
sì, ma
è
guarda,
online.
giro con questi, sì, non
Certo.
non c'è problema. È sempre complicato queste cose.
Sì,
alla
poi da quando
fine.
c'è Zoom è diventato
Sì,
ancora
sì,
più, più la charge di stress.
No, noi a Stoccolma
Uh-huh.
abbiamo pure noi ibrido, quindi Zoom, eccetera, e la cosa strana da noi è che la stanza cioè, è random, cioè lei ogni giorno cambia quello che funziona e quello che non funziona.
Ok.
Certe volte la telecamera non funziona, certe
Ah,
volte
ok.
il microfono non funziona, certe volte funziona tutto. Come gli pare quello?
E ti trovi bene a Stoccolma?
Sì, mi piace.
Fa freddo?
Sì, però mi
No,
piace.
non è per indipendente da quello. Però il riscaldamento globale non è ancora arrivato lì.
Guarda, secondo me è meno forte lì. Cioè non è come sul Mediterraneo che genera questo calore dal mare. È meno sì, meno, cioè loro dicono che comunque è cambiato, cioè c'è meno neve, è un po' diverso, però comunque la differenza è minima. Invece se io penso a Roma, come è cambiato il tempo a Roma da quando ero piccola, secondo me è diversissimo.
È diversissimo.
Sì.
This one is more basic.
Ah, this is the...
Yes, but you have a USB.
Yes. Sì.
So that one, if you put slide, you should the laser, of course, and you can go
Okay, perfect.
down. Okay?
Thank you.
Merci beaucoup.
Yeah, perfect.
But from remote, there's no one for the moment, so not an issue.
Hello. Bonjour.
Bonjour.
Et comment vous faites là?
Ouais, bah sinon j'attends moi je démarre et puis après je m'en vais. Je comprends pas tout.
No. Sei mai stata a Stoccolma?
No, mai, infatti mi piacerebbe andare. Però ho diversi amici che sono passati di là.
Oh, scusa, ti ho interrotto.
Non era importante. Ah sì, no, che ho visto le pubblicazioni recentemente con tante persone, perché succedeva in America, ma lì.
Sì, diciamo questo lavoro qua, cioè il gruppo adesso stiamo lavorando molto in gruppo.
E il PI chi è?
Jens.
Ah, ok, non lo conosco.
Sì, lui è islandese,
No,
lui è
c'est pas
stato
possible.
negli Stati
Oui.
Uniti e
Ah, bah, c'est
a
bon.
Dresda.
Ah,
Elle a son propre.
Bisogna fare l'annuncio.
ah, non puoi farlo tu, no? Lo faccio io, ok?
Perché
In inglese o in francese si fa l'annuncio?
in inglese.
Solo. In inglese?
In inglese solo.
Aspetta che mi cerco il
Eh.
il titolo e ora.
E adesso dico.
Ok.
Now. Ciao. Sono Riccardo.
Très rapidement, le truc c'est qu'elle va faire des slides, donc elle va se mettre en mode slide avec la petite caméra en bas. Et puis ce truc, il faut faire attention, c'est si le speaker il bouge trop, pas qu'on le perde. Et c'est le truc, il faut faire attention.
Oui.
Tu te mets pas trop loin
Ah,
de...
oui. Non, mais attends, j'ai pas le droit de...
Oui, je sais.
J'ai compté les boire là.
Mais t'as entièrement raison.
J'ai juste mis les pieds. Lo faccio io, dai, ho bevuto il caffè.
And it's also streamed on YouTube.
Ah, ok.
It's online.
So I see the names there, and they
If
they
their picture will be above. Yes, it's to announce. But this one should work, but it doesn't work, c'est un problème, je pense.
Ah oui, j'avais jamais vu celui-là.
Ouais, bah, s'il y a un incendie, ça veut dire que vous êtes à fond dans votre truc et vous n'entendez pas et vous volez tous.
En grille.
Mais enfin, je rappelle que la dernière fois, quand il y a eu un alerte incendie, personne n'est sorti de cette salle. Et moi, je me suis fait allumer parce que je suis animateur de sécurité, je me suis fait allumer.
Tu viens d'arriver, c'est pas juste maintenant.
Ah, j'ai pas entendu.
Il faut l'envoyer sur YouTube.
Ça y est, c'est fait?
Ti prendi tu la posizione di controllo.
Ah non, en principe, c'est sur le aussi. Vas-y, va ici, je me page toute prête. Va ici. En principe, ça diffuse sur YouTube et ça fait 5 minutes qu'on a commencé. Je sais pas où faut le voir, live. Vas-y. Bah oui, j'ai fait streaming.
Oui, mais il y a la clé.
Oui. C'est sur mon compte, vas-y, fais les settings. Ah non, tu peux pas faire les settings quand c'est chaud.
Ça, c'est le compte à qui?
À moi. Bon, je vous laisse démarrer.
Voilà, IPHT-TV.
Je vais voir de mon côté. Je vous laisse.
Ok, et là, en théorie, ça va marcher. Bon, on laisse tomber. Alors, le son est bon, et tu peux aller.
Okay, so hello everybody. Today we have the pleasure to have Claudia Artiaco from the Royal Institute of Technology in Stockholm, where she is doing her postdoc. Before she was a PhD as TISA in Trieste, and she has worked on disordered systems, both quantum and classical, today in a broad sense. In particular, she has worked on quantum jamming and many-body localization, and more recently she has been interested in the dynamics of quantum systems, also with dissipation, and she has studied also the topic of thermalization and the dynamics of information. This will be the subject of this talk.
Yeah.
Thank you, Claudia.
So thank you very much for the introduction and to all of you for coming. So today, as Laura was saying, I'm going to talk about the time evolution of local information. So we have two concepts here in the title, and I will go in more detail into these two concepts of time evolution of quantum many-body systems, and in particular of this local information, which is a quantity we introduce, we define, which is a measure of entanglement. So it is a joint work with many collaborators at KTH, and it is now on the archive, and it is related to a previous work by Thomas, Jens, and Loic. So, as I said, one of the main concepts I'm going to discuss is the concept of entanglement. And entanglement, which in a famous quote by Schrödinger, is the characteristic trait of quantum mechanics, and I I will show in which sense I mean this, in particular in my perspective, and also the concept of information, which is physical, and I think in this talk, in some sense, we really see why we can say it is physical, at least from this perspective of time evolution. So, in particular, I will discuss entanglement in the sense of, from the perspective that it really poses significant challenges when you want to simulate the out-of-equilibrium dynamics of many body quantum systems. So, in particular, one of the concepts many people talk about that is related to this challenge is the presence of the so-called entanglement barrier. So the idea is that during time evolution, entanglement, if you have interaction, so many body systems, entanglement spreads. And this means that if you want to represent the exact state at long times, you need to have an exponentially large number of parameters because of the Hilbert space, because the Hilbert space dimension increases exponentially with the degrees of freedom. But there are two limits in which we can actually do an efficient representation of the states. And two cases are when you have product states, which is typically the initial state from which you start your time evolution, and when you have Gibbs states, which are thermal states, so when the system appears locally thermal, so when quantum thermalization has happened, and in this case you can efficiently represent the state. So this is exactly the idea of this entanglement barrier, in the sense that if you quantify the complexity of your simulation as a function of time evolution of the system, you see that the complexity is low when you start, because you usually start from product states which are low entanglement. Then at very long times you have, if the typical system thermalized, so you reach a thermal state, this is still very easy to represent because you can parameterize them with local observables. And the problem is the interpolating between these two regimes. And this is what is called the entanglement barrier. So we don't really, this is exactly the out of equilibrium dynamics that we don't really know how to do, because we cannot, we cannot do large systems because of the Hilbert space, exponential increase of the Hilbert space dimension. So the idea of this talk, what I'm going to propose is an approximate time evolution scheme which tries to interpolate between these two limits, so to overcome the entanglement barrier. But to do so, I have to introduce an abstract construction, which is a new construction of entanglement, like a new way of understanding entanglement, which is a bit abstract, and then I will go to something which is more concrete, but I have to ask you to follow me in this abstract definition. So first of all, I want to redefine entanglement, like what is entanglement in quantum systems. So the idea is that if you have a composite system which is composed by two pairs A and B, the Hilbert space of the composite one is the product of the Hilbert spaces, and then you have an operator, a density matrix for the composite system, which is an operator that acts on the composite Hilbert space, the Hilbert space of the composite one. And let's assume for now it is a pure state, so the full system is pure. Now the problem, the definition of entanglement, the very definition is that if I cannot write ρ as a product, as a tensor product of the subsystem density matrices, the reduced density matrices, by definition, ρ has entanglement between the two parts. And so what it means is that if I know the reduced density matrix of one of the two subsystems, I can compute any observable on the subsystem. So if I know ρ A, I can compute any operator that acts on the Hilbert space of the subpart A. But if I know ρ A and ρ B, I cannot in principle reconstruct exactly what is ρ of the composite one, of the full system. So which means that basically entanglement is non-local information.
Sorry.
Yes.
Is the assumption of pure state important in these statements?
I mean, it is important in the sense, as far as I know, there are no non-known and mathematically rigorous definition of entanglement measurements if you have mixed states. Yeah.
Okay.
And in my
Naively, I thought that this could be the definition, but it does not work for general rho, it means.
Yeah. So the definitions, I mean, for example, the entanglement entropy, you have many properties that derive from the fact that the full system is pure, and then you can say something about the entanglement entropy in the subparts, for example.
Okay, thanks.
So now I want to introduce another related quantity, which is the von Neumann information. So let's say that now we have a chain, so we go with a more concrete example. This is a chain of spins degrees of freedom. And I want to look at the subpart A, which has extension LA. So if the reduced density matrix of rho A is pure, then in principle I have access to log 2 to the LA bits of information, where 2 to the LA is the Hilbert space dimension of this subsystem A. So this is the situation in which, in principle, I have access to all the information in the subsystem. When instead, in the opposite case, rho A is fully mixed, so it is proportional to the identity. This is fully mixed in the sense it's fully a statistical mixture, which means that I don't have access to any bits of information because it is probabilistic in a classical sense. And the von Neumann information is basically a measure that interpolates between these two limits. And it is just the Shannon information of classical information theory. So it is defined as the log of the Hilbert space dimension, this log 2 to the LA, minus the von Neumann entropy, which can be defined for any reduced density matrix. This is standard definition of the von Neumann entropy that you have already seen. So we see that this quantity is non-zero in this case and is maximal, while it is zero when I have a full mixed state. So it's really interpolating between these two cases when I have access to the information and when I don't have access to it. But now my question is, what is the distribution of information in a given state? So now I want to use this quantity to understand more in detail what is the spatial distribution of information in a generic state, which is quantum, of course. And to do so, I want to use the simplest example to introduce to understand a bit what I want to construct, which is the singlet. So now I just consider only two spins, which are in a singlet state. And then I ask myself, what is the von Neumann information if I consider the reduced density matrices? And then what I see is that from this state, if I construct the reduced density matrix of one single spin, the first A that I call here A or the second B, I see that this is fully mixed. So basically it's saying that at the local level, I have zero information, which is here. So von Neumann information is zero. When instead I go to the two-side case, so I really consider the state of the two spins, I see that the von Neumann information is log 4, where 4 is the Hilbert space dimension. And now, to understand why this is crucial, we can make another example, which is the opposite case, in which instead the composite system is fully mixed. And now, if I look at the reduced density matrices, I get exactly the same answer, because the reduced density matrices are still fully mixed, which means that at the local level I still have zero information, which is exactly the definition of entanglement in some sense, no? Because even though I know there is entanglement here, if I look only at the single spins, I cannot distinguish at the state of the single spins, of course, I cannot distinguish between the two cases, which are very different. But instead, if I consider the two-side state, I see a big difference, because now I have log 4 for the von Neumann information in this case, while I have 0 in this case, because it is fully mixed as we saw before. And now I want to introduce the quantity I used in my title also, which is this local information. So what I do now is that I say, okay, I see there is this hierarchical structure, so there is it changes, the von Neumann information is different if I consider only one spin or if I consider 2 and so on. So what I say is that I take my physical chain and I call this level 0, and I say, okay, I can consider each spin individually and compute the state of the single spins, but at the same time I also want to introduce another dimension, which is labeled by this scale L, in which I say, okay, but I can also consider the subsystem made of the 2, which in this case is the full system. And in the simple case of the singlet, so if I have a singlet state, I define now the local information, which is just the mutual information constructed by the von Neumann information we defined before. So, and if I now measure the local information for the singlet, what I find is that, mutual information means that I have to look at the information of the composite system minus the one that I found in the reduced ones, and then I have to resum the overlap part just for counting reasons, basically. And in the case of the 0 level, it just, of course, these are empty sets, so it is just the von Neumann information we computed here, and this is 0. But then for the singlet, I get that this is exactly log 4, so it is non-zero. And of course, now I want to generalize it because I'm interested in chains of more than 2 spins. And let's look at another very simple example, which is the case in which I have a product state of neighboring singlets. So I'm just doing the same construction. So I have a physical level, which is this level 0. And then I have also many other levels which represent the subsystem made of neighboring spins of any length I can have, in the sense that the first level is still representing the subsystem made of 2. So this point represents the subsystem made of these 2, these of these 2, these of these 2. But I also have a third level, L equal 2, so a third level, in which this represents the subsystem made of these 3 and so on. And if I now compute this local information for this very simple case, since these are just singlets, they don't share entanglement. They don't share entanglement at a scale that is larger than 2 spins. So I just get this the same local information here. Then here I don't see anything because there is not a singlet between these 2. But then there is this singlet, and I get log 4 here again. Okay, and so maybe this is not that clear because we haven't used higher levels. But now if I consider a random singlet, which is a bit more complicated, so I have singlets not between neighboring pairs, but between random spins in my chain, I see that I also have turned on some higher levels, no? And the reason is that, for example, I have a singlet that is between the edge spins, which are connected. I see them together only if I go to the top level, because I really have to consider the full chain to see the entanglement between the 2. And there I get exactly log 4 local information here because of the singlet between these 2. Okay, so this abstract construction is finished, more or less. But now my question is the time evolution, right? So now what I want to do is say that I want to understand how the spreading of entanglement, so the entanglement barrier basically, appears in my local information triangle.
So, as I understand, you introduced this local information. Do you have, there are some kind of geometrical inequalities for entropy or like convexity?
Yeah.
Did you check all this? Or?
Yeah, there is. there is one very important property. Thank you very much for the question. So there is one very important property, which is that the sum of over the full triangle of this local information, it's very easy to check because it's just mutual information, so you have to subtract the subsets and so on. It is equal to the von Neumann information of the full state, which, if the state is pure, is a number, is log of the Hilbert space dimension. And this is, this is conserved because it doesn't change if the system is, if you evolve under unitary time evolution, the system is always pure. So the sum is conserved, which means that I define basically a conserved charge for information, which means that I can define currents, which is what I'm gonna use.
Okay.
Thank you. Okay. So and now I want to see my entanglement barrier in this framework. What I do just for the sake of simplicity, I take just some random brickwork of independent random unitaries, which is like the simplest many-body dynamics I can think of. For now, I'm not interested in any specific Hamiltonian. And so now let's see what happens in my information lattice. I start with a system of Tate spins and in a product state. And if I use my definition, I see that at the initial time, so for this state, I have local information only at the level of the single sides. But then, under time evolution, which means in this specific case, under the application of the cycles here, I see that it is spreading to higher levels. So higher level in the hierarchy means longer distances in the physical axis. So this is exactly how the entanglement spreading looks for me. The sum over the full triangle is always conserved, but this charge is moving up.
Sorry, there are always 18, or you reduce the number? How
No,
many?
it's always 18.
Okay.
So each time I go one level up, the reason why it is a triangle and not a square is that each time I go up, I reduce by one, just because I can group them in neighboring subsystems made of, for example, made of 2, only L minus 1 times, and so in the end, I get a triangle.
Okay, but they are random. The choice, no, they are not random.
These are random.
Okay. So the B, C, and D are random evolution. There is a component of random evolution.
Yeah.
Okay.
Yeah, this is because I can do exactly the same picture with an Hamiltonian, which is like a many-body Hamiltonian. I didn't want to. Okay. This is just because it is the most generic. You may by this gates you make the degrees of freedom interact. So it's just a generic interacting evolution. So, but the main message here is exactly the fact that it's going up. And now I want to go back to my practical problem. So I want to find this approximate scheme for time evolution. So I go back to my construction. So I'm just saying I can construct. So my construction is for subsystems. So I can take my physical chain and construct a subsystem of neighboring sites, which are L plus 1, so are like defined by this label L, and also they have some position in the physical chain, which is this N, which is just the center of the subsystem. And so I can do this. I can do this recursively and from my physical chain construct this big structure. And the way in which I want to use this for time evolution is that now I want to write the von Neumann equation. Just rewrite the von Neumann equation for the subsystem, such that in principle, I have many parallel evolutions for reduced density matrices. So I can say, okay, I consider the system CLN, I take the von Neumann equation, which would be just the T rho is equal to minus H rho, where rho is really rho of the full system. And now I just trace the complement of the subsystem I'm looking at. So, and I get this. And the reason why I get, so I get again the term, basically the same term you see usually in the von Neumann equation, just because the Hamiltonian, I mean, it has interaction, but it also has interactions among the degrees of freedom of this CLN. For example, if we look at this purple triangle, this term is giving me the fact that the evolution of this state here is determined by the Hamiltonian terms that are within these sides, but I also have the interactions with the other sides that are outside the triangle I'm looking at. So I have also for example, if I have nearest neighbor interaction, which here means this R is equal to 1, I also have terms that connect in the Hamiltonian between these two and between these two, which means that in my equation of motion, I have these other two terms, which says that if I want to do the time evolution of this, and I have nearest neighbor interaction, I also have to consider the state here, one level up, and going up means going, extending in the physical direction. So I have to go one level up because I have also to consider this interaction term between these two. Okay? So this is exact. It's just rewriting the von Neumann equation. And since it is exact, I haven't simplified the problem. So it's not my approximate scheme. I'm just rewriting it. And the problem is that you see that this is not a non-closed hierarchy. And the reason is that if I know the state at some time, 0, let's say, I can make if I know rho at time 0, I can construct all the reduced density matrices, because I can always go down. I can always trace out and know the states of the subsystems. But, so I know, in principle, I know the state here at time 0, the state here at time 0, and also here, so I can make one time step. But then, when I want to make another time step, I also have to evolve the higher levels. And in the end, I have to go up to the top of the triangle, so I'm not simplifying. But now there is a concept that helps us to try to close this equation to this hierarchy. So we want to close it because basically we want to reduce the complexity, no? So we have to evolve subsystems that are smaller than the biggest one. And we can use these PETS recovery maps, which are a quantum information concept. I mean, it's been introduced in quantum information theory. And the idea is that the idea in the end is quite easy. So it's just that if there is no information on the higher scale, which means there is no entanglement, from the reduced density matrices, so from the lower levels, you can reconstruct the higher level. And this is exact if there is no information on the scale that is higher, which is exactly the fact that if there is no entanglement, I can, from the reduced density matrices, I can reconstruct exactly the state of the composite system. But so the problem is that for this to be exact, I need to not have entanglement that is shared between these two subsystems. And so, okay, I can try to use this for my time evolution, and I can slightly simplify it. So I can say, we said we start time evolution from entanglement that is a low scales, right? So I can always solve this equation by putting myself at a level, L star, in which there is no information. So I solve this, I make one time step using this equation of motion, and then for knowing the higher level states, I just use the PETS map, and I say, okay, but if I need this to make a further step, because I need to know this at t plus dt, then I just use what I have just computed to reconstruct the state, which means that I can, in principle, try to stay at this level and close the equation of motion here. But the problem is that, as we saw, there is entanglement goes always up. So if I want to maintain this exact scheme, I also have to increase my scale constantly. Okay. And so now it enters our truncation scheme, so our way for approximating the time evolution. The time evolution. So the idea is that it comes from basically thermalization in quantum systems. So the idea is to say, for a generic many-body Hamiltonian, I expect thermalization to happen. And thermalization means that I know that at very long times, locally, I would see a thermal state, which means that the entanglement is low. So in thermal states, I have volume law of entanglement, so entanglement is huge, but it's at very large scales, which increase extensively with the system size. But locally, you always see a thermal state. So what it means is that you don't really need to know the exact state, all the details of the state at very large scales. So you can forget about the details and just locally you wouldn't see a difference, okay? And so the idea is that we say, okay, but we can minimize the information at a certain level, and by minimizing, I use minimizing as a synonym for removing. I will explain, I hope, more in detail clearly. So I want to minimize information at a given scale, so really to remove it at a scale that is the largest that I can do, of course, in my computer. But of course, I also have to keep some constraints. So I also want to keep the lower level density matrices and also the information flow fixed. So when I do this removal, which it is a large scale, I don't want to ruin what is at lower scales, because I'm interested in the end in local observables. And the way in which we do this is that we say, okay, we know the state rho ln, and we have to shift it, so we have to modify it, adding this chi, which is an Hermitian matrix, but this chi needs to preserve the properties I was saying. So I need chi to not change the lower level density matrices, and you can, I mean, it's easy to show in the end that this is just given by these two conditions. So I want the reduced density matrix when I trace out one spin from chi to B0, but yeah, I don't want to go in this detail now, just that this constraint is fixing the lower levels, states. And I also, and this is crucial, I also want to keep the flow of the information, and this is crucial because I don't want to know exactly what is in highest levels, because I cannot access them, but also I don't want to stop this flow, because I expect, my assumption is that entanglement also spreads, so it goes up. So I really need this second condition. And then the minimization is just saying that I want to minimize the information, so I want to maximize the entropy. So I need to find chi such that this is maximal. Okay? So, and pictorially what I'm saying is the following. It's saying that I'm going to change the state at some level L min, but I keep fixed what is in this gray area, and I also keep fixed these arrows, which are a representation of the currents of the information, the local information. And the reason why I can do this is because it is conserved, so I can compute the currents of this entanglement, basically. And so now a pictorial representation to try to explain a bit more about these constraints. So when you do the minimization, you go from some profile of the information per scale. So you can measure the information per scale, for example, integrating in the horizontal axis. And you modify the profile, so you really remove the information. So you go, for example, in this sketch way from the azure to the yellow. But the problem is that if you keep only the constraint 1 and you don't use the constraint of the flow for the flow, here you are decreasing the information, which means you also decreasing the currents, and so you have this build up here of information at lower scales. So you are modifying also the lower levels. So you are, I mean, it's more likely that you are going to introduce some backflow, okay, because you are not keeping the flow as it was naturally. So when instead you use the two constraints, these two, you still modify the profile, so you reduce the information from the blue to the yellow, but you keep the currents. So the idea is that you don't stop the flow, even though you are modifying the states. And so now this is basically the representation of our scheme, which is that we have to do some loop kind of thing. So we want to do, what we have to do is to have a way for estimating the currents. So we perform the time evolution at some higher level, so at another scale L max, which is not L min. And then once a small amount of information is accumulated at the level at which I'm time evolving, since I'm using PET's map for time evolution, so these are wronger and wronger if there is too much information. When I see there is too much, I have to minimize the information at L min. And I do this in this cyclic way. So I can also just say I always time evolve at some level which is the highest I can reach with computational resources, my computational resources, but and then I do this removal at a lower level. And the reason why I do at a lower level is because I need to know the currents. So I need to let information flow to estimate them. Okay, so I just want to show some results we got with this scheme. So this is the first thing we measured was the energy diffusion in the mixed field DC model, which is an interacting model, and for some specific values of the parameters. And the reason is that we wanted to compare with the tensor network methods, which are, the state of the art of tensor.
By the way,
yes.
which kind of numerical tools did you use to solve that?
It's just Runge-Kutta integration of the equation of motion in parallel. So you have to do for many.
But when you compare with tensor network state-of-the-art methods, it's for the same model, but I suppose it's not with the same modelization as with your entropy, or?
Mm-hmm. Yeah, sure. So the one I'm gonna compare with is this paper, which is, as far as I know, the state-of-the-art for thermalization, like for this kind. They have, in principle, tensor networks who work very well when entanglement is at low scales. So in this state, what they call state-of-the-art, these are new proposals which use tensor network ansatz plus additional things. For example, in this case, they have what is called dissipation assisted method. So they introduce a dissipation which does something that is similar to what I do with my minimization.
Okay. Sorry, can I ask, why don't you take the integrable case that you can solve, or your scheme doesn't work for integrable?
No, I could do that. The point is that I know many people test tensor networks for example, the easing without interaction. But the point is that this is really a many-body scheme, so it doesn't really make sense to test it for something that is integrable, I think. So this is the reason why we made many more simulations for this case to really check how much we could push and compare. Yeah. So, and here what we did is that because of the fact that we solved this von Neumann equation, we have a choice that is particularly clever for the initial state. And the cleverness is the fact that if I initialize the system at infinite temperature everywhere, this is identity matrix, so it's not evolving. But then I perturb it in the center, and I inject some finite density of energy, so this is perturbed. So what I do is that in the end I'm simulating an infinite system, but what I do in practice is that I always track only the center, and then I enlarge the system because I mean this energy diffuses, so I have to enlarge it. But these data are basically for an infinite system. I mean, this is also something tensor network can do in some cases, but not in this. No, I mean, also in this probably did that. But anyway, so what I measure is the spreading of the energy and the diffusion constant of the energy. And I do this, I need some parameters to see the convergence of this diffusive process. So there is, first thing, I see diffusion in the sense I expect this system to have diffusion for the energy, for the conserved charge, which means that I expect the diffusion coefficient to be constant, and I see that, I mean, it has a slight drift here when this length is small, but then it goes, I mean, it becomes more flat as I increase the scale, which is my real finite size, basically, that I have to consider for convergence. And then from this data, I can also extract what is the value of the diffusion coefficient in the asymptotic limit, like for infinite length. And I compare with the one that they measured, which is 1.4, but I mean, something that has to be noticed is that they could arrive only to time 20, so they couldn't reach larger times, while I could reach 100 here. So they were in a regime in which, from my data, it really seems the diffusion was not converged. So if I compare to this number and I extrapolate my value for different max length, but also extrapolating as a function of 1 over L mean, I see that I get a larger value, which is 1.55, which is actually going slightly down for increasing L max. So I get a difference, which is order of 10%, but yeah, so this is the comparison we can do with the caveat that the timescales we could reach are very different. And then I can also import, this is an important check, I have to check that I really get diffusion, so that the power law exponent for this expansion, for the spreading of the energy is 1. And if I extrapolate the value still, I mean, for a larger, the longest time I can reach, and for the largest scales I can reach, I see that it is very, very close to 1. It's, yeah, which is the value I expected. And so this is not a trivial result, in the sense that it's not easy to get diffusion when you do a full quantum simulation, because of quantum, I mean, the entanglement barrier, basically. So, but now I think I was too slow, so just want to say that we also use this code to reproduce some experimental results for a system that is much more complicated. So it's actually a diamond in which you have a nitrogen vacancy that you excite, and then you look at the magnetization relaxation of these isotopes of C13 isotopes. And the system is driven by a Floquet drive, so it's very different. But when we put ourselves to the pre-thermal plateau, and we take a simplified model which has a diffusion, a similar Hamiltonian, which is in 1D and with only nearest neighbor interactions. So much simplified. But when I use an Hamiltonian that mimics the diffusion process they have, and I also introduce Lindblad dissipators, which I can do for free because I'm solving the von Neumann equation, so I'm using density matrices already. If I consider this diffusive process plus dissipation, I could reproduce the behavior that we're seeing, which is the onset of a gradient of polarization, which is stable over time. And then just want to mention that apart from this time evolution application and our approximate algorithm, also this abstract construction, the information lattice I constructed at the beginning, is very useful if you want to understand the quantum phases of matter. So if you want to see, for example, if there is localization, if there are Majorana states. So we tested this for something, but unfortunately I cannot go in more details. So I just want to say for statics it's also useful, I think. And so just to sum up, I introduced this light approach, which I call light because of local information time evolution, which I think is really powerful in the sense that we can simulate very large systems for very long times, and we are not, I mean, it's valid for generic local Hamiltonians with a finite range of the interaction. So we tested it for diffusive systems, but we can also try and for super-diffusive and ballistic, and it should work very well, and also probably when the spreading is lower, it works as well. And also the other very important thing is that it's applicable to open systems with the Lindblad master equation. And the other thing was this information lattice for statics. So thank you very much.
Are there questions?
How large system can you reach in spatial dimension?
Yeah. So for this data in particular, at the largest times it was order of thousands. My bottleneck is more this length, this level, because that if I go one level higher in my demonstration, I get a factor of 4 of memory. I need because I use density matrices.
Questions?
When you simulate a system with this method, what are the density matrices you really have in the computer?
Mm-hmm. Yeah. So okay, let's try from here. So what I don't know, maybe it's better if we take the von Neumann equation actually. So what I do is that I fix a level L star, which is L max most of the time. I mean, and then let's say that I know the state of L max and also L max plus 1 at time t. Then what I do is that I integrate this with Runge-Kutta integration, and so I know all the density matrices at level L max, for any n at level L max at time t plus dt, and then I have to do PEX map.
You know the ones at lower levels?
Yeah, the lower are always known because okay. you use traces and you can always go down. The very problem is to go up. So I have to use the new state at the level L max to reconstruct the states at level L max plus R, where R is the range of the Hamiltonian. In the case I was showing is 1. So I use this to reconstruct the highest such that I can make another time step basically.
Okay, I'm not sure I got it. But so at the end you get you have all the density matrices up to some level L max or L max plus 1, and the lower ones. Okay.
I always have.
So
Yes.
it scales exponentially in L max.
Yes,
Okay.
exactly.
If you had to say in 2 words why it is so powerful in terms of reaching big systems, and is just because you have a strong, let's say, definition of local entropy, or what makes it so efficient?
I mean, I think what my feeling is that what makes it efficient is actually just a change of paradigm in some sense, which is not unique. So there are also other methods that are going in this direction, which is the idea that if you want to simulate thermalizing systems, you have to understand that locally you don't really need to know exactly the structure. I mean, to reconstruct the local observables, the local states, you don't need the exact structure at very high levels, like at very large distances, just because this does not affect the expectation values locally. And this is really thermalization. So I would say this, and then in our specific case, I think it's really the local information itself, because it's very nice to understand really how entanglement is spreading, not just saying it increases, but really knowing where it's going locally. Yeah.
Could you say a bit more about these other methods which go in that direction?
Yeah, so there are, for example, the method I was comparing with in these slides, this one. This is what I've never used them, so I just read. So it is an MPO method, so they also use MPO matrix product operators, so they also evolve density matrices, and they do something which is very similar, which is to remove entanglement by having how do you say, like not fake, but like some synthetic dissipation process, which is not physical, but is doing what we do. So it's removing the information that you don't need, that entangles very distant in space degrees of freedom. So the tensor networks that are going in this direction add some unphysical dissipation process or mixing process, such that you remove the large-scale entanglement. So there is this paper, and there is another paper by Marie-Carmen Bagnol, which is from, I mean, they probably posted it in August, which is different from this one, but is still a mixing of the local density matrices.
Okay. So yes, in between this one and yours?
Yeah. The spirit is similar. And I think this is the direction, actually. Not necessarily mine, but the direction of using the very concept of thermalization. Of course, then if you don't have thermalization.
Okay, no, thank you.
Thank you.
Can I ask maybe a question? So at the beginning you have the sketch of a complexity barrier.
Yes.
You could, that was the sketch, but you could somehow extract it from your simulation. This.
I mean, no, in the sense that I try to overcome it by reducing the complexity in some way, you know.
Okay.
I mean, I might, yeah, I don't think I can estimate, in the sense that it's true that I know this flow.
No, isn't it? Just curiosity. Okay, thank you.
Thank you.
T'as même pas le temps de manger?
Non, c'est pas ça, j'ai un rythme à moi.